Okay, so far we've been looking at the benzene ring and what happens when we put a substituent on a benzene ring, how to put them on there. What if the benzene ring already has a substituent on there and you want to put a second, maybe a third one on there? What effect does a substituent on a benzene ring have on the placement and the reactivity of that benzene ring for new substituents? We'll look at that now under E substituted benzene rings. And the first thing we need to look at are inductive effects. Because if the atom is more electronegative than carbon, it's going to pull electron density out of the ring. Look, nitrogen's more electronegative, oxygen's more electronegative than carbon, pulls electron density out of the benzene ring. Now, the problem is that makes the benzene ring a little less reactive because recall in the mechanism of electrophilic aromatic substitution, the first step is the pi electrons of the benzene ring must attack the electrophile. If you take some of the electron density out of the benzene ring, those pi electrons don't have as much negative charge. Some of it's been taken away. They're not nearly as nucleophilic, and so they're less likely to attack an electrophile. So the nitrogens, oxygens, these type of elements uh, pull the electron density away, make the ring less reactive. Alkyl groups, on the other hand, are polarizable and they are electron donating. A methyl or an ethyl group actually donates electron density to the ring. So a methyl group adds electron density to the ring, making it more nucleophilic. But these groups here are what we call electron withdrawing groups. All right. But there's another effect that actually is more important than the inductive effect, and that's resonance effects. As we find out with resonance structures, they kind of dominate chemistry in terms of make resonance structures mean something's more stable, reactions more likely to occur if the product has resonance forms, less likely to occur if the reactants have resonance forms. So resonance always very important in organic chemistry. So let's look at these important resonance effects here. So when you look at a nitrogen, or it turns out an oxygen that has a lone pair on it, it turns out that lone pair can, through resonance, be delocalized onto that ring. This lone pair, if we formed a double bond here, would put a negative charge here on the ring, or here, or back to where we began through resonance. So it turns out this nitrogen, while it is electron withdrawing because it's more electronegative than this carbon, and you would think it would pull electron density away from the ring, when you have a lone pair on that nitrogen, as they most likely do, that is going to add electron density to the ring through the resonance effect, through these resonance structures. If we see a carbonyl bonded to a benzene ring, and we look at its resonance forms, note that when we look at all the resonance forms here, we put positive charge on the benzene ring. We take electron density away from the benzene ring, which makes it less reactive. And so while you must consider both, when you have something like aniline here, the inductive effect with the nitrogen pulling electron density away because it's more electronegative, and the resonance effect putting electron density back on the ring, it turns out the resonance effect is the most important one. So we can summarize that with this little chart down here. If you have an alkyl group, there's no resonance. The carbon of an alkyl group is sp3 hybridized. To get resonance forms, you need an sp2 hybridized carbon. So alkyl groups are only electron donating just because through inductive effects, alkyl groups are electron donating. But anytime you have some atom Z that has a lone pair on it, then that resonance effects will overcome any inductive effects, and so these are all electron donating groups. Electron withdrawing groups, a halogen, there's no resonance effect to put the electron density here from these lone pairs on the ring, so it's just inductive effect pulling electron density away from the ring. or anytime you've got a group on the benzene ring that can have some sort of partial positive charge or full positive charge, those are electron withdrawing groups. Okay. And we are going to summarize that in a table in just a few minutes. So then, how do these electron withdrawing groups and electron donating groups, how do they affect the reactivity of these rings? Okay. Well, it turns out electron donating substituents, these guys up here, as we said, they add electron density to the ring, make the ring more nucleophilic, more negative charge, more likely to undergo electrophilic aromatic substitutions. And because of that, and as we can very easily see when we have a lone pair and we looked at the resonance forms here, we can see that the negative charge goes ortho to the substituent and para to the substituent, which means when you have a group like aniline, the two orthocarbons and the paracarbon are more electronegative. They have more electron density. They're not more electronegative, excuse me. They have more electron density on them, pi electron density on them through this resonance effect. So the new substituent will go ortho or para. So, summarize that here. Electron donating substituents activate the benzene ring, make it more reactive, and they direct the next substituent to be ortho and para. For example here, here we have phenol, and we know that this oxygen has two lone pairs on there, so we know, okay, it's an oxygen with lone pairs. This is going to be an activating group and an ortho pair director. So if we add Br2, FeBr3, we're going to get a bromine ortho to the OH, and we'll also get a molecule with the bromine para to the OH. So you will get both the ortho and the para products, two products. Now, that being said, due to steric hindrance, a bromine's a pretty big group. There's a bit of steric hindrance here. In general, you will see more of the para product. Anytime you have this situation where the product can go ortho or para, in general, you see more of the para. But I'm sure there are ways that we can make it have more ortho. People in chemistry always say, all right, if this is the way nature wants it, let's find a new way to make it go the other way. Okay. When we look at our electron withdrawing groups, such as carbonyls, they deactivate the ring. They pull the electron density away from the ring through resonance, and they will direct the substitution to the meta position. Because if you recall from previously, when you have an electron withdrawing group, ortho and para have positive charge. So then it's the two metacarbons where the more electron density is, and so that's where the substituents will go. So if you have this group here, a carbonyl with a CH3 on there, put Br2 and FeBr3, we know this combination of reagents adds a bromine. We know this is a meta director, and so the bromine will go meta. Now here's the thing. Electron withdrawing groups, such as carbonyl groups, such as this ketone here, deactivate the ring. However, just meaning it's deactivating just means it reacts more slowly. It doesn't completely stop it. It just means this ring is less reactive now that this carbonyl is on there. So this reaction would occur much more slowly than this reaction here. Electron donating groups activate the ring. This is going to be a faster reaction. Electron withdrawing groups deactivate the ring. This will be a slower reaction, but you still can get it to occur. All right. Now, halogens are electron withdrawing. There's no resonance, and so their electron density pulls the electron density, their electronegativity pulls electron density away from the benzene ring through the inductive effect. So they're weakly deactivating. They're not strong deactivators because there's no resonance. They're weakly deactivators. However, they actually direct substituents to the ortho and para position. So if you start out with a bromobenzene and you add Br2 FeBr3 to add the next bromine on, even though this ring has been deactivated a little bit, the next bromine will go ortho and para. You'll get a molecule ortho and a molecule para. In general, you'll have more para than ortho, but you'll get both products. Okay. And the nice thing is, in your book, there's a really nice table for the, what is this, the 5th edition of Smith, page 701. Just memorize, get this table memorized right here. Well, there it is. So this just tells you, this table here tells you what goes on. Where we have our increasing activation going this way, where R meaning just normal alkyl groups or weakly activating. This group, the acid analide, is what we dealt with in the lab, is more active. OR, they make the ether is even more active. Phenol would be more active. And then nitrogen. Nitrogen with lone pairs, be it primary, secondary, tertiary, aniline or aniline derivatives, are very activating, very strongly activating. Benzene rings with amines on them are extremely reactive, very strong activating group on here. Methyl groups just weakly activating. And all of these are ortho and para directors, including the halogens. The halogens fall under this part here. They're ortho para directors. However, note they are also deactivating. The halogens are weakly deactivating, followed by aldehydes, ketones, esters, carboxylic acids, the cyano group to make a nitrile, sulfonyl, nitro group, and they're getting less and less reactive, more and more deactivated as we go down. So nitro group is a very strongly deactivating group. Here we have a nitrogen with 3 other substituents on it, the 4th being the benzene ring. So a nitrogen with 4 covalent bonds has positive charge on it. Very, very strongly deactivating with that positive charge on there. Okay, but this is a nice table to know for the next exam, which is coming up. All right, so back to the notes. We do have some issues, however. There are limitations to these reactions. And we're going to look at some of them. Get that camera straight again. There we go. All right, limitations of electrophilic aromatic substitution with substituted benzene. Limitation number 1, halogenation of activated benzene. Recall we said that aniline here, this NH2, makes this a very strongly activated benzene ring. It is so strongly activating, it is so reactive that you put Br2 and FeBr3 in there, you should get a tribrominated aniline. In lab, when we did the relative reactivity of aromatic compounds, those with aniline should have noticed 3 bromines on their aniline and as a product of the reaction. OH, oftentimes with OH, if you have a phenol, you get 3 bromines on there. Esters, such as anazole, you should probably find 2 bromines on there. Okay. And acid analide, recall from our table here, acid analide is kind of weakly deactivating, so you'd only expect 1 group there, on that 1 bromo group there. All right, so that's the first. When you halogenate activated benzenes, very strongly activated benzenes are going to get multiple halogens put on there. You can't stop it. It just is going to happen. You cannot stop aniline from putting just one bromine on there. Now, here's something we need to get straight in our heads, because someone might say, yes, but what if I only put enough bromine to get one bromine put on here? Because wouldn't I have to add a whole bunch of bromine to get 3 on here? The answer is, if you just put a little bromine in here, if you make Br2 the limiting reagent to do this reaction, what you're going to find is you're going to end up with a mess of products. You are going to have some aniline that only has 1 bromine on it. Some aniline will have 2 bromines on it. Some of the anilines will have all 3 bromines on it. And there'll be a whole lot of unreacted aniline if you made Br2 the limiting reagent. So all of a sudden you've got the monobrominated, the ortho, the monobrominated para, the dibrominated, the tribrominated, and the excess aniline. That's 5 different compounds, all with very similar polarities, all in your reaction mixture there. It's going to be extremely difficult to separate them, and so synthetically it's just not viable. You're going to have to throw away 95% of your reaction to get that to clean out that one product. So you just can't do that. You cannot use Le Chatelier's principle. You cannot use limiting reagents to limit this reaction, because you'll just end up with a mess if you try to do that. All right. Other things we have to worry about with Friedel-Crafts. If you have here, okay, here's nitrobenzene. We know the nitro group is a very strong deactivator. If we tried to run a Friedel-Crafts reaction, we'd get no reaction, because it turns out the electrophile you make with Friedel-Crafts is just not a good enough electrophile to attract the pi electron density of this benzene ring when you have such a strong deactivating nitro group on there. If there's a carbonyl on here, which is deactivator, you probably still could do Friedel-Crafts, but not with a nitro group. A nitro group is too strong a deactivator. This benzene ring is just too unreactive to do a Friedel-Crafts reaction. And then something weird happens, because you start to think, okay, if a strong deactivator here means this ring isn't active enough, isn't reactive enough to do Friedel-Crafts, then a very strong activator here should do Friedel-Crafts really well. Turns out nitrogen aniline groups on here, amines, do not do Friedel-Crafts also. Because the problem here is this is a strongly activating group, but a nitrogen with 2 electrons is just a very, very strong Lewis base. And AlCl3 is a really, really strong Lewis, a really nice Lewis acid. So what's going to happen, instead of your acid catalyzing the reaction of putting the alkyl group on the benzene ring, your nitrogen of your aniline just attacks your catalyst and kills the catalyst. And without catalyst, you can't get, you can't get the reaction to go. Not only that, but the product has got the nitrogen on here with a positive charge now. It's deactivating. All right. Another Friedel-Crafts issue is polyalkylation. Now, if you just take normal benzene, put RCl, AlCl3, like a methyl or an ethyl, just normal ethyl or methyl group on here, you'll get that ethyl methyl group on here. But now note, this is an activating group. Alkyl groups are mildly activating, which means this benzene ring here is more reactive than this benzene ring, which means as these two, the original starting material and this product, will then compete for the RCl that you put in there for the alkyl halide, but this is more activated, so it's more reactive, so it will have to put that second R group on there. And truthfully, these two now have 2 activating groups on there, so they'll start adding a third R group on them. They'll try to do that. So because of polyalkylations, regular old Friedel-Crafts is not the easiest reaction to carry out and get the product you want. So how do you get the product you want? What if you wanted to only put 1 methyl group or 1 ethyl group or something on there? Well, instead of doing a Friedel-Crafts alkylation, you'll do a Friedel-Crafts acylation. Because check this out, you take your benzene ring, you put your acyl group on here, RC double bond O. Note, it's a carbonyl bonded to a benzene ring. This is a deactivated benzene ring. So you do not get polyacylations. So this is a deactivated benzene ring. So what if you wanted to change this? What if this was CH3 C double bond OCl? So now you have carbonyl CH3. What if you wanted to change it to CH2 CH3? What would you do? That's right, Clemmensen reduction. Clemmensen reduction. Amalgamated zinc with HCl. Or perhaps Wolff-Kishner, hydrazine and base. All right. So now that we've got, we start with a benzene ring. Previously, we found ways to put one substituent on a benzene ring. Now we've seen how that one substituent affects where a second substituent would go. What if we already had two substituents on the benzene ring? What happens then? Well, we'll look at that in the next video.